When someone is asked what they want to do with their life, we're used to a familiar response. I want to change the world. I want to make an impact. While there's certainly many people who have made extraordinary contributions to society over the course of their lives, some names stand out more than others. Names that are connected to deeds or inventions that are so great, or in some cases so horrible, that it's unlikely that they'll ever be forgotten. One of those names, without a doubt, is the physicist Albert Einstein. Einstein was born in Germany in 1879. As a young adult, Einstein moved away from his home country to Switzerland in order to attend university. His desire for more expansive and innovative learning methods had already gotten him kicked out of school in his native country. Switzerland, however, proved to be the perfect place to expand his thinking. The only way humanity has gotten anywhere was by asking questions, and Einstein knew exactly which questions to ask to fundamentally alter the way we view reality. Soon after his move to Switzerland, he began contemplating the movement of light and questioning the very laws of physics that governed the world at the time. In 1905, Einstein had what is now known as his Year of Miracles. In the span of a single year, he released 4 separate publications that very well changed the landscape of science forever. While each paper is extremely important in its own right, it was his 3rd article, on the electrodynamics of moving bodies, that had the most striking impact on the world. This was the birth of Einstein's special theory of relativity. Einstein's theory contradicted 2 of the most well-known theories of physics at the time, Isaac Newton's concepts of absolute space and time, and James Clerk Maxwell's theory that the speed of light was a constant. His paper proposed that time passes differently depending on the speed at which someone is moving relative to someone else. This theory is known today as time dilation. Time dilation says that an individual in inertial motion will experience time differently than a second inertial individual who happens to be in relative motion to the first person. To make that a lot easier to understand, let's take a look at the example Einstein himself used to explain his theory. Picture yourself on a train. It's moving much faster than any train has moved before, and as you zoom past the surrounding landscape, you see that you're approaching a train platform where your friend is standing, waiting for you and the train to pass. As far as you're both concerned, you are each standing still. The difference is, of course, that you're inside of a fast-moving vehicle while your friend is on the outside of it waiting on the platform. Easy enough. Now imagine that, just as the center of the train passes by your friend, lights at both the front and the back of the train light up. Knowing that light always moves at the same speed, and because both lit up at the exact same distance from your friend on the platform, the light would reach your friend's eyes simultaneously, and they would tell you that they witnessed them light up at the exact same time, and they would be right in saying this. Now, if your friend saw the lights turn on at the same time, the same thing should be true for you, right? Interestingly enough, it isn't, and here's why. We know light travels at the same speed no matter what, but remember, you're on a fast-moving train, so to you, the light at the front would appear to turn on first, because the train is rushing to meet it. Meanwhile, the light at the back of the train would appear to turn on just a moment later, because it has to catch up to the train speeding away from it. The thing is, you would also be correct in your point of view. But how can this be? How can you both be correct in observing the same event differently? Einstein's theory also introduced the idea of length contraction. Because we know that speed is determined by distance over time, it would follow that in order for the speed of light to remain constant, the other 2 factors must change to accommodate that constant. We've already talked about how time can change depending on your movement, but distance always changes depending on the movement of each inertial figure. For example, let's put you back on that train with your friend on the platform. This time, your friend got a bit stronger, and is now holding up a canoe that stretches 100 feet long. Now, to your friend on the platform, it's clear that they're holding a canoe that's 100 feet long. Because they're standing still, it's easy to see the length. If they took a measuring tape to it, it would measure 100 feet exactly. Now cut back to you standing on the train as it rushes past your friend. That canoe is going to look a whole lot different to you. As you pass it at an unimaginably fast speed, the canoe will appear much shorter than its actual measurement. So, which is real? Well, again, the answer is both of them are. The length of the canoe doesn't actually change, but the perception of its length appears shortened or contracted to you from your position in the moving train. The faster you move, the shorter that canoe will appear. While this sounds like an interesting experiment to conduct, the speed that humans would need to travel at to see noticeable differences is not a speed that we can realistically achieve. Einstein showed that no object with mass can ever surpass the speed of light. The heavier the mass, the harder it is for it to accelerate, so experiments like this one are gonna have to be put to the side. Now, just as with time dilation, these observations are only noticeable at speeds that move at a substantial fraction of the speed of light, so these aren't observations that you and I will be able to make in our everyday lives. However, they have been tested many times throughout the last century and still stand as some of the most important contributions to physics in history. Remember that at the beginning of this video, I mentioned that 1905 is referred to as Einstein's Year of Miracles? Well, this is because he produced one final paper that year that arose out of his special theory of relativity. This paper, which some say was actually just a note jotted down in the back of a journal, proposed that energy equals mass times the speed of light squared. Or, in the equation known around the world, E equals mc squared. This equation states that energy and mass can be interchangeable, so if mass is converted completely to energy, it can wield a tremendous amount of power. A common example of this is how an atomic bomb can be so incredibly powerful and destructive. This idea led Einstein to publish yet another groundbreaking theory in 1915, known today as the general theory of relativity. The general theory of relativity was the result of Einstein's continued thinking on how his theory of special relativity related to non-inertial frames of reference, as in areas that accelerate relative to each other. Einstein's findings showed that gravity, the force that is working constantly to pull objects towards each other, is actually warping or curving space and time. The bigger the object, the bigger the curve, and because we know that objects with mass are drawn towards each other, the object with the bigger mass is always more powerful. That's exactly how we end up with orbits. Planets and stars alike fall into the curves that their bigger counterparts create. For example, the Sun is much more massive than the Earth, and so it warps space-time much more, which grants it a larger gravitational pull. You can keep going with this idea and deduce that the whole universe exists within a system of these curves of the fabric of space-time. Isaac Newton, more than 200 years earlier, had hypothesized that an object thrown with the perfect amount of acceleration would begin to curve around our planet. With the right set of initial conditions, it could potentially remain in an endless loop, spinning around the Earth due to the sheer force of gravity constantly pulling it in at the perfect curve. What he was describing essentially was orbits, the exact thing that the International Space Station is doing above our heads right now. However, Newton saw acceleration and gravity as individual entities, while Einstein's theory showed that acceleration and gravity can be interchangeable. This idea is known as the equivalence principle, and it dictates that you cannot tell the difference between the effect of gravity and the effect of being in an accelerated frame of reference. This principle is often demonstrated by having you imagine that you're in a room with no windows or any way of knowing where you are. If you were to drop a ball in that room, you can imagine that it would fall at the rate of gravity, 9.8 meters per second squared. But if you were to drop a ball on a rocket ship that was accelerating at exactly the same rate as gravity, it would be impossible to tell whether the ball was moving down because of the Earth's pull on the object, or just because the floor of the rocket ship was rushing towards the ball due to the acceleration. Einstein's theory of general relativity helped to explain how our universe works. Because of his contributions, we can predict the path of asteroids in the orbits of faraway stars. This theory can even be applied in some of our favorite films, as special effect engineers can calculate exactly how objects move in relation to each other, even in the most unlikely circumstances. Since the publication of Einstein's theory of general relativity, there have been many experiments conducted that have proven that his findings are in fact correct. Some were done during Einstein's time, while others continue to this very day. One of the most famous confirmations was Einstein's correct prediction that Mercury's orbit would change its arc by 43 seconds each century due to the curvature of spacetime. And he was accurate. Extremely accurate. In fact, he was actually able to prove the very thing that was predicted by Newton, but that couldn't be solved with traditional Newtonian mechanics. In another test in 1919, an English astronomer by the name of Arthur Eddington set out to prove Einstein's prediction that light rays bend when they're close to a large body. He did this by looking at the positions of stars in relation to the sun during a solar eclipse. After looking at the positions of a certain group of stars both during the eclipse and at another time, Eddington saw that the light from the stars had been deflected by an amount directly in line with Einstein's theory. While Einstein's papers were certainly extraordinary, it still took some years before his theories were widely accepted. However, as test after test continued to confirm his predictions, the skeptics slowly diminished. In his later life, Einstein moved to the United States, where he continued to work as a physicist, focusing predominantly on an attempt to find a unified field theory. Unfortunately, he wasn't able to complete his work before his death in 1955, but his final paper helped lay the groundwork for future physicists to complete his mission in finding a unified field theory, more commonly known as a theory of everything. Reconciling both quantum mechanics and general relativity may turn out to be one of the most challenging feats science has ever taken on. But as always, if you give us enough time, we'll slowly chip away at the problem, week by week, year by year. And who knows, one day in the not-so-distant future, we may just find the master key to the universe. What happens after we unlock it? Well, only time will tell. This video was sponsored by Brilliant. Brilliant hosts some of the greatest math, science, and computer science related educational content on the entire internet. It's extremely interactive, with over 60 courses either having code to write, puzzles to solve, or some other challenge to overcome. They're constantly adding new courses and finding new ways to challenge your brain. For example, if you enjoyed this video, they have a course on special relativity, which will teach you the ins and outs of Einstein's greatest work. Seriously, I actually used it to help write this video. Brilliant has courses that cover almost any science-related interest you have. It's definitely worth looking into. They'll rewire the way you approach problems, connecting the numbers and theories you learn to actual real-world examples. If you or someone you're close with is interested in having a big impact on the future, you'll be surprised at how easy Brilliant makes it to learn things. It's amazing for people of all skill levels, novice to expert. If you're one of the first 1,000 people to click the link at the top of the description, you'll get 20% off a premium subscription, and you'll be able to take every single course Brilliant has to offer. In reality, it's an amazing deal. Whether it's for yourself or a gift for someone you care about, there's loads of value there, and I highly suggest you check it out.